On this video, we're going to go over the notes on waves. So a wave is a disturbance that travels from one place to another with no actual transport of matter. They're going to transport energy. A lot of waves are going to travel through what's called a medium. A wave medium is a substance that carries a wave from one location to another. It can be a solid, liquid, or gas, or some combination of these. The medium itself is not actually the wave, it's just what the wave travels through. So don't confuse a medium for a wave. Right? A wave, again, transports energy and not matter. And some waves don't require a medium to travel through. They can travel through a vacuum, which is empty space, like outer space would be that. Right? Now let's move on to some categories of waves. So we can categorize waves in two different ways. We can do it either by how the medium's particles move, or we can do it by its ability or inability to transmit energy through a vacuum. So if we organize them by how the particles move, we get longitudinal waves, transverse waves, and surface waves. If we instead do it by the ability or inability to transmit energy through a vacuum, we're going to categorize them into two things, which would be electromagnetic waves and mechanical waves. Right. So now let's talk about each of those types of waves. So first up is longitudinal wave. A longitudinal wave is a wave in which individual particles of a medium vibrate back and forth in the direction that's parallel to the direction in which the wave travels. These can also be called compressional waves, is another term for these. But if you picture this diagram here, say if these dots all represent the particles in the medium. If this wave were moving to the right, these dots would be moving left and right back and forth as this wave travels to the right. If you picture this diagram down here as a slinky, like all these little waves are the coils of the slinky, and you're sending like a pulse through that slinky. So the slinky coils like group up and then spread apart, and then group up and then spread apart as it travels down the length of that stretched out slinky. Excuse me. Also, sound waves are an example of a longitudinal wave. Okay. Next up is transverse wave. Transverse wave is a wave in which individual particles of a medium vibrate side to side in a direction that's perpendicular to the direction in which the wave travels. So if you picture this diagram here, these are all, again, the medium particles. If this wave were moving to the right, these particles would be going up and down. So the wave travels this way, and then the particles are going perpendicular, which would be up and down. Okay. And an example that's not written here, but an example of this would be like if you took a piece of rope and you shook it up and down, like and it would make this pattern when you do that, that would be a transverse wave. Next, we have a surface wave. A surface wave is a wave in which the particles in the medium undergo a circular motion as the wave travels through it. So, for instance, ocean waves or waves in a lake as a boat passes through, those are going to be a surface wave. So these dots here represent the medium particles, and they're going to follow that path of this line here as it moves through it. Okay, and we're not going to focus too much on surface waves, but just so you know what they are. Right. Next, in our other way of categorizing waves, it's going to be mechanical waves. Mechanical wave is a wave in which the wave cannot travel through a vacuum. So they do require a medium to travel through. So for instance, sound waves, water waves, a wave through a slinky or through a rope are going to be mechanical waves. Sound waves require a medium. They cannot travel in outer space. For water waves, your medium is the water. For a wave through a slinky or a piece of rope, those items are the medium. Okay. Then the other type of wave is electromagnetic waves, and those can travel through a vacuum. So for instance, they can travel through outer space, and they do not require a medium. Examples of these would be light waves, X-rays, UV light, radio waves, and there's a handful of other waves that we'll learn about a little later in this unit. Okay. Moving on to the anatomy of waves, we're going to look at longitudinal and transverse waves a little bit more. So for transverse waves, this diagram down here is similar, is the diagram you need to know. There is one thing missing off the labels here, which is equilibrium or rest position. That's this line here through the center, and that's the position the medium would be in if there were no disturbance moving through it. So if you picture this wave as a piece of rope, if you weren't making a wave through the piece of rope, it would be just a straight line, right? The crest is the highest point in the medium from that rest position. So all of these peaks here are your crest, and then the troughs are the lowest point in the medium. So that's these valleys here, okay? Then we have the amplitude of the wave. That's the distance from the rest position to the crest or to the trough. So you can see that here measured. Normally it goes from rest to crest. just because that's fun to say. For transverse waves, the higher the amplitude, the more energy the wave is going to have, right? And then wavelength is the length of one complete wave cycle. So for this, it's like if we start here at the beginning of this, go up to the crest and then go back to the rest, then go to the trough and back. That's one complete wave cycle. And then this one repeats about three times in this diagram. So that we could measure wavelength from the start here to the start of the next one. An easier way to do it is generally going from crest to crest or trough to trough, just because those are easy to spot on the diagram and measure it that way. Right? Be sure you're able to identify and label a diagram like this on any quiz and test in this unit, because they will show up. Right? For longitudinal waves, they're a little easier to do. There's not less things to label. They have compressions, which is where the medium has maximum density. So if you picture this as a slinky, and these are all the little coils, and you're sitting like a pulse through the slinky, where they're grouped together the closest, or maximum density, that's a compression. And then where they're farthest apart is called a rarefaction. So if you think rare, they're far apart, hard to find, whatever. Wherever the slinky coil would be farthest apart would be your rarefactions. For the wavelength, that is one complete cycle of a wave. And the easiest way to measure this on a longitudinal wave would be compression to compression, because those are easiest to spot on the diagram. You could technically also go rarefaction to rarefaction if you wanted to. All right, moving on to a few other things involving waves, which would be frequency, period, and wave speed. The frequency of a wave is the number of waves that pass a particular point in a unit of time, and these are going to be measured in hertz, which is abbreviated Hz. It's named after this guy here. It's technically 1 over a second. But if you think of frequency, it's like if you were sitting at the beach and you counted how many waves crash on the shore in a certain amount of time. That would be the frequency of how frequent is this happening, okay? Then we have the period, which is the amount of time required for a wave to make one complete cycle. So we talked about that term period back in circular motion, was like the period was once around the loop, essentially. So period here is one complete wave cycle, right? And it is measured in seconds. And period and frequency are related mathematically. The two formulas here, we won't really use these too much, but they are pretty simple to use when needed. But period here is abbreviated with a T and frequency with the F. And if you had the frequency and needed the period, it's 1 over the frequency, and then 1 over the period to get the frequency. Okay. And then we have wave speed. Wave speed is the speed at which the wave travels at. Its formula is frequency times wavelength, and that's abbreviated right here. For the units, frequency again is in hertz, wavelength is in meters, and then for velocity or wave speed, it's going to be meters per second. Because like I said earlier, frequency is technically 1 over a second. So when we multiply that by meters, that gives us meters per second. Okay, and I'm not going to do an example in this video because I think at this point in physics, you should be capable of multiplying two numbers. If not, we really need to work on that. Now we're going to get into behavioral waves and just give a brief overview of a few different behaviors. So the first one is reflection. It's probably one you're familiar with, but reflection is the bouncing back of waves upon reaching another surface, like light striking a mirror and bouncing off, or an echo would also be an example of reflection. Then we have refraction. Refraction of waves involves a change in the direction of waves as they pass from one medium to another. And this will cause a change in wave speed and also a change in the wavelength of the waves as they travel between mediums. An example of this, you can see a few different ones in these pictures here. But as waves travels like from air through the glass into the water, it can cause things to be distorted. Like here we see it looks like these straws are broken, or this duck looks like it's cut in half, or like here we see like the sphere fisher, he thinks that the fish is here, but in reality it's here. So it just can cause things like that. And there's other examples of this out there. It's kind of a neat phenomenon, I think, of just how it changes things. But that's refraction. Then we have diffraction. Diffraction is the bending of waves around a barrier, such as an obstacle or edges of an opening. An example of this would be sound waves traveling on a doorway and spreading into the hallway. So like if I was teaching right here in the classroom, and then my voice is going to carry out into the hall, and it's not like they're just going to keep going straight and you can only hear me talk straight ahead. People over here can hear me because that sound wave is going to spread out once it gets to the hall, right? And you can also see that here with water waves, or on this Google Earth image, like we have like a barrier islands here, and you can see the little ripples in the water of the waves, and they're coming in, and then you see that nice curve in there of them bending as they travel to the shore. Right. Next, we have wave interference. Wave interference is the phenomenon that occurs when two waves meet while traveling along the same medium. So if you think of a piece of rope and one person shaking it at one end and one person at the other end, and then where they meet, they're going to have interference. And there's two types of interference. There's destructive and constructive. Destructive, if you kind of think destroy, they're going to be opposites, and it's going to not always cancel out the waves, but a lot of the examples you'll see in diagrams is them canceling out. And then constructive is like, if you think construction, they're going to build each other up. So they're going to have the displacement in the same direction. So what that means with this displacement term, like if you look at these diagrams here, constructive, we have the red wave and the blue wave. They're traveling opposite directions. They're going towards each other. And their displacement here is both in the down direction. Okay, so like if you think their troughs are combined, are in the same together. So when they combine, like these ended up with the same amplitude originally, so it ends up doubling the amplitude, and so the green wave is the interference that they create. Right? So red plus blue, since they're the same amplitude, they end up doubling the total amplitude at that moment. So the green is the actual wave versus destructive. The red wave and the blue wave, they have a displacement in opposite direction. Red's up and blue's down. And these happen to have the same amplitude. So when they cross paths, it ends up canceling each other out. So we get this green wave here. Okay. All right, let's go on to Doppler effect. Doppler effect is the apparent change in pitch or wave frequency due to a moving wave source. If the wave source is approaching you, like think of a siren from an ambulance or a cop car or other emergency vehicle. If it's approaching you, it's going to have an upward shift in frequency. It's going to sound like a higher pitch to you. When it's moving away from you, it's going to cause a downward shift in frequency or a lower pitch. All right. And then you can see that here in this diagram here, as the ambulance is approaching, it has a shorter wavelength. And then when it's traveling away, it has a longer wavelength. And I 100% certain you've heard this in real life, but you just didn't know what it's called. But if you're not sure what I'm describing here, I would recommend going on YouTube and typing Doppler effect and listening to an example of it, because it would hopefully click then for you. Right? Pitch is how high or low a sound seems to be. The pitch of a sound is related to the frequency of the sound wave. As the frequency of a sound wave decreases, the pitch is going to be lower. And for you singers or band students, you've probably heard this term before. Right? Next, we have a standing wave. That's a wave pattern formed in a medium when two sets of identical waves pass through the medium in opposite directions. So in this example here in this diagram, it's the rope is tied to something, so it ends up reflecting back. But you could do this from two different points, like two people holding each end of the rope and shaking it, matching up, but it's easier to create with one end tied to something. But anyway, you shake the rope and it ends up creating this standing wave pattern. And then in this wave pattern, you have two different things. You have areas that look like they're not moving, which are called nodes. So like here, if we have like kind of two bubbles here, a node is these points where it just doesn't look like it's moving. And then the areas where they're like the rope is essentially farthest apart in the bubble as it moves would be your antinode. And we won't deal too much with this right now, but anyway, last thing is resonance. Resonance is when an object's vibrating at the same natural frequency of a second object, and it forces that object into a vibrational motion. So with tuning forks, if you have two of the same frequency, you can sometimes get this to work. But another example that's common in TV, when a singer hits that really high note, their sound waves they're producing from their singing is at a certain frequency that matches a glass, and then that glass starts vibrating, and then that causes it to shatter because it can't handle the vibrations. But that effect you see in TV and movies and stuff is resonance, right? But that's the end of this video. Let me know if you have any questions.